Okay, so in this chapter, so on the last chapter, you learned about energy, which is a scalar quantity. In this chapter, we'll learn about a quantity called momentum. Okay, we'll learn about linear momentum. Okay, and momentum is mass times velocity. So we'll learn about linear momentum. And linear momentum is a vector quantity. It's denoted by P, and it's the mass times velocity of an object. And you can see that this is a vector quantity. A scalar multiplied by a vector is a vector, so it's a vector quantity. And the units are kilograms, meters per second. Okay. All right, well, why do we learn about this? Let me show you a simulation. Okay. So we are going to make these two objects collide. Okay. So the mass of object 1 is 0.5 kg, the mass of object 2 is 1.5 kg, and we've given it certain velocities. I don't know where the velocity adjustment is. Anyway, so we've given it certain velocities, and there is the momentum of object 1, and there's the momentum of object 2. And there's the total momentum. The total momentum is just the sum of those two vectors. Okay? And this is a 1D collision. You see, after the collision, their momenta changed, but the total momentum remained the same. Okay, so let me redo that. Okay. And I can change the mass to whatever I want. Okay. I'm going to redo this. And so, okay, there you go. There's the total momentum, and watch for the total momentum. Okay. And the total momentum remains constant. Okay, so we are going to learn about momenta, and it's a useful quantity. So in physics, you see all kinds of complicated motion, and you want to see what remains constant. So we learned that total energy remains constant for an isolated system, and now we're learning that total momentum will remain constant for an isolated system. And so that constrains the possible type of motion. Okay, so that's what we want to learn. Okay. So one of the ways collisions, accidents are analyzed is they know momentum before the collision is equal to the momentum right after the collision. Okay, and so that's the rule we're going to learn. So let me show you another simulation. Okay, we've all played pool. Okay, and so this will all happen very fast. And this is on a pool table. It's an elastic collision, almost, you know. And what we mean by an elastic collision is, what does an elastic collision mean? Where's my mouse? I don't see my mouse. Anybody see it? Oh, there it is. Okay. So when he shoots the cue ball, it will have kinetic energy, and that kinetic energy will be imparted to all these balls. And if it's an elastic collision, the total kinetic energy will remain constant. Yeah. And if it's not an elastic collision, then some of the energy gets converted to other forms, but total energy will remain constant. And what will remain constant, what is conserved is when you shoot the ball, you give it a momentum. So this system has a total momentum of just the momentum of this ball. And after the collision, the total momentum of all the balls will be equal to the initial momentum. So you see that's a pretty powerful statement. When you break this rack, the total momentum afterwards is precisely equal to the total momentum before. The rack was broken. Okay, so the rack cannot randomly break. It's got to break such that the momentum is conserved. Okay? How long is the momentum conserved? Till one of the balls hits the side rails. Okay, so you have to have an isolated system. Okay, all right. So I mean, I'll show you the breaking of the rack. So what we now learned is that when you shoot the ball, cue ball, you have given it a certain amount of momentum, and that momentum will be conserved even after the collision. Okay. So I'll try and catch it.
Not the most pretty rack you see. That right there is how you're supposed to rack the ball.
Okay, I couldn't catch it. All right. So that's what we're going to learn in this chapter. Okay, so we are going to learn about linear momentum, and the linear momentum of a particle is denoted by P. It's a vector quantity, and it's given by that. Okay, and we'll see that in collisions, linear momentum is conserved, and it's a very powerful tool in analyzing collisions. Okay, so so these are the topics we'll cover: linear momentum, collisions and impulse, conservation of linear momentum. Okay, again, we are always looking for conserved quantities because that restricts the type of the motions that a system can take. Okay, so if you have to conserve kinetic energies, let's say this guy's two cars of equal masses collide. Let's say two pool balls of equal masses collide. This guy's going at 10 meters per second. This guy's going at 5 meters per second. You know that after the collision, because kinetic energy has to be conserved, none of them can go faster than 15 meters per second, right? So that's the kind of statements you can make. Okay. All right. So conservation of linear momentum. Okay. And we'll look at momentum and kinetic energy in collisions. Okay. All right, so here are two objects colliding. So let's say this guy is going in this direction. This guy comes and collides with him. So his momentum is that's his momentum. There's momentum of ball P1, momentum of ball P2. The sum of these momenta is that's the total momentum. After the collision, this guy is going in that direction, this guy is going in this direction. There is P1, P2 prime, but their sum is still the same. The momentum is conserved. Okay? And this will always be true unless they have rockets attached to them. And rockets, when you attach rockets, now you're applying an external force. Okay? So we'll learn about that. So if there are no rockets attached, the momentum is conserved. Okay? So in this chapter, we define another conserved quantity, linear momentum, which will put an additional constraint on how a system evolves in time. Okay? Conservation of momentum is useful for understanding collisions. Yeah. Momentum is just as powerful, important, and useful as energy. Yeah. Again, I hope you guys understand the fact, so let's say energy is conserved, momentum is conserved, and then if you can come up with other quantities that are conserved. So for instance, you learn about angular momentum that's conserved. So the more and more quantities that are conserved, the less and less possible types of motion you can have, right? Do you guys understand? What we are ultimately about is describing complicated motions. We want to understand them. Okay. And so if you can say that something is conserved in a complicated motion, then you're learning something about a system. Okay. So linear momentum. Okay. So here's a situation. So here's a situation that just Newton's laws will not help. I mean, Newton's laws are not enough to solve a problem like this. See, when the bat hits the ball, the force is not constant, and the force changes very fast. So for instance, the force that the bat exerts on the ball is like this. It's zero before, the force is zero before the ball comes in contact, then it'll rise up and then go down like this. Yeah. And at the peak, the force that the bat exerts on the ball can be 3,000 times the weight of the ball. It can be very large. Okay? So in most sporting events, that's the kind of forces that happen. Okay? So just using Newton's laws won't help us solve it. Okay? So here's another thing you'll learn in this chapter. In one of the previous chapters, we applied forces that change with distance. Okay. Forces that varied with spatial coordinates. So here's a situation where forces are changing with time. Okay. So careful. What was this area?
Work.
Very good. Who said that? Very good, my friend. This area was work done by the force. And what did work do for you? It changed kinetic energy. Yeah. This area, it turns out, is called impulse. Okay. It's denoted by I or J in some books. Okay. And what does this do? This changes linear momentum. So this is a vector quantity. Okay. So very similar theorem as last time. Okay.
Is it just more work, or is it?
No, well, this is changing linear momentum. It's not. So this is not work. This is. It's got different units. This thing is called impulse. Okay. So what are the units of this area? On the y-axis, you have Newton. Newton second is the unit. Newton second is the units for this guy. Okay. For this guy, it's Newton meter, which is joule. Okay. All right. So I'm giving you information from all over the chapter. Okay. So. Okay, as the situation arises. So often we encounter situations where the applied force varies with time and is non-zero for extremely short intervals of time. So for instance, this base bat is in contact with the ball probably about 50 to 100 milliseconds, 50 milliseconds, okay? Same for golf. For a soccer ball, it's a longer collision because the soccer ball is softer, okay? We have several athletes on our team. You're a soccer player, right? Yeah. You just do track? All right, so the harder the ball, the smaller the collision time. Okay. So to analyze such situations, it's convenient to define a quantity called linear momentum. So linear momentum is denoted by P. It's a vector quantity, it's mass times velocity. What is Newton's second law? You guys remember? So force equals mass times acceleration. Okay. So that is the baby version. Okay, here's Newton's, the real version. So here's Newton's second law. Okay. So let's see how do we get that other quantity that we always learn. Okay. So force is so it's really time rate of change of momentum. Momentum is mass times velocity. Okay. And from the chain rule, you've learned dm by dt times velocity plus m times dv by dt. Okay, so force is that. All right, so why do they say this? Well, in most situations that you encounter, the mass of the object does not change. So dm by dt is zero. So in most situations, that's zero, and so you say force equal to mass times acceleration. Yeah. Are there situations where the mass changes?
Yes.
Yeah. What?
I mean, the first one that comes to mind is a rocket.
I'm sorry?
A rocket.
A rocket, right. So in a rocket, the mass, it burns 90% of its mass is burned, 90% is fuel, and it burns it very fast, okay? So this term is sizable, in fact, this term can be larger than that term, okay? So there you cannot ignore it. But when you're driving your car, you're burning maybe 3 gallons of gas over an hour, and that's nothing. So this is very small compared to that, okay? So in most situations, this is the predominant term, and this is thrown out the window, okay? But there are situations where this can be larger than that, okay? All right, so from now on, when somebody asks you what's Newton's second law, F is dP by dt is the answer, okay? All right, so now let me put that Newton's second law. What is Newton's second law, my friend? Oh, there you go. See, you're a quick study. All right, dP by dt. Okay, so what this is saying is change in momentum over change in time, over the time over which that change happened. Okay, so what this is saying is, so if you had a momentum and then you want to stop it, so that you know the change in momentum, the faster you want to stop something, the greater the force you have to apply. Smaller this guy is, greater this has to be. Okay, so here are some momenta given, and so 90 miles per hour fastball, it has that much momenta, and when the catcher catches it, he catches it, and so he stops it in a certain amount of time, and he's got to apply force. What does he do if he doesn't want it to sting? Right, you take a recoil. What are you doing by doing that? By when you recoil, you're increasing the stopping time, and that doesn't sting, okay? So it's all in the equations, guys. Okay? You just have to figure it out, okay? And so also, what does an airbag do? Yeah, it increases your stopping time. If the steering wheel stops you from 80 miles an hour to a rest, it's stopping you very fast, and it applies great forces on you, which is not good for your health. So an airbag, an airbag will increase the stopping time. Okay. Okay, so that's what safety devices are about. Okay, so the idea of a safety device is to increase stopping time. Okay. So if you increase stopping time, if you increase that, forces acting on you are smaller, right? Thereby reducing the force one experiences. Yeah. A steering wheel would stop you very fast, whereas an airbag increases stopping time substantially. Okay, so you guys have all heard the word impulse, but now we'll give a quantitative meaning to it. Okay, so the impulse approximation. Okay, so let's say we are playing golf. So here's the club, here's the ball, here's the tee. Okay, right now, what are the ball forces acting on the ball? Gravity. Normal force. And right now, that's it. Okay. And once the club comes in contact, well, those guys are still there. They haven't changed much. But now this guy's come into play. And this guy can be very large. At the peak, like I said, it can be as large as uh, 1,000 times the gravitational force. Okay, so essentially, well, these two forces are canceling, but when this guy is talking, you can ignore everybody else, and that's the impulse approximation. Okay, when the big dog talks, okay, everything else can be ignored. Yeah. So in many situations, a single force acting for a very short time is the predominant force. Okay? In such situations, for this short period of time, all other forces can be ignored. Okay? And now, so this is the force that the club exerts on the ball. And what we're going to do is we're going to say something about the area under this curve, which we already did. Okay? And that's the big theorem in this chapter. Okay? So you saw that when forces change with distance, the area was called work. Area under that curve was work, and the work showed up as change in kinetic energy. When forces change with time, the area under the curve is called impulse. And what an impulse does is it changes the momentum of the movement. Okay? All right, so this area is called the impulse. So the only difference between Tiger Woods and me is his impulse is a lot greater than my impulse. Yeah. All right. Okay, this uses a vector notation. I don't want you to get confused, so we'll consider one-dimensional case. So the force is in one dimension, so dp by dt is ft. Okay? And p is a function of time as well. Okay. Now here's an equation. This is Newton's second law. When is it valid?
It's an isolated.
No, it's valid all the time as far as we are concerned. Okay. We're not going to talk about electrons and stuff like that. We're talking about cars. We're not talking about super fast moving stuff. So for massive objects moving slowly, this always applies. Okay, so this is an equation and it's a law of physics. And you can hit the left-hand side with the hammer, the right-hand side with the hammer. Okay, and the fundamental theorem of calculus says, okay, this is just Pt initial to final. Okay, the fundamental theorem of calculus, the integration undoes the derivative. And that, on the right-hand side, is the area under the curve. Okay, so this is P final minus P initial. And that area under the curve is given a name, so I'm using J. Some textbooks use I as well. Okay, so whatever they call, impulse or J, I or J. Okay, so this area under the curve is PF minus PI. Okay, so here's what I mean. Okay, PF is MV final minus MV initial. So if you're playing golf, the ball is sitting on the tee box, and that's 0. Okay, and so now you see what I mean. The greater this area, the greater the velocity of the ball it takes off from the tee, and the further it goes. Okay? So a professional imparts a large impulse. Okay? Did you guys understand that? Okay. All right. So oftentimes you can't measure the details of the force. We will do a lab where we will measure this force. We'll measure, and this is the best experiment you'll do. And we'll measure the force that's imparted 500 times a second. Okay. So that'll be the most accurate experiment you do. All right. Most situations you're not able to measure the details. So what we're interested in is just the average force. Okay. The average force is defined as it lives as long as the original force. Okay. and the area, this area is equal to that area. So that's the definition of the average force. Okay? So oftentimes we're just interested in that. And again, in most sporting events, how long does the force live? How long does this live? I'm sorry?
Couple milliseconds?
Oh, more than, yeah, 50 milliseconds in baseball, for instance. Okay? Okay. So that's the kind of stuff. Okay. So this time is about 50 milliseconds. All right, you guys understand? All right, so here's Newton's second law again. Net force is rate of change of momentum. Okay, and this you'll learn in a second. This applies to a single particle. It applies to a system of particles. So the net force is sum of all the forces acting on the system. Okay, net force is internal forces plus external forces. What are internal forces? So for instance, when this ball is touching that ball, they push each other. Those are internal forces. Or if they're charged, they'll attract each other and so on. So those are internal forces. But Newton's third law says for every action, if this guy exerts a force on him, he exerts an equal and opposite force. So if you add those two up, this will always add up to 0. And external forces, Daniel pushing on this guy, okay? And so those will be the external forces, okay? So if you want to change the momentum of this system, what you have to do is apply external forces, okay? Only external forces can change momentum of the system. So for instance, the cue ball was sitting on the table. If you want to change the momentum of the cue ball, what do you have to do? You have to use a cue stick. You're applying an external force, okay? So external forces are what change the momentum of the system. So for an isolated system, there won't be any external force. This will be 0. dP by dt will be 0. So P is constant. Again, that was the statement. And that's what you saw in simulations. Okay. So for an isolated system, now you've learned two things. Okay. No matter how complicated the motion. So for instance, the gas in this room, there's 10 to the power of 28 molecules. This is an isolated system. Now you can say two things about it. You know that its total energy is conserved and its total momentum is conserved. Okay. Did you guys understand that? All right. So here are situations where you can apply this. Okay, so here is a kaon. It's a neutral kaon. Okay, so this is a very short-lived particle, and you can look up its lifetime in Google, for instance. Okay, and let's say you make this in lab and it's at rest, and within probably a microsecond it'll break up. It breaks up into two pions. These are particle-antiparticle pairs. They have equal masses, opposite charge. See, the initial momentum was 0, and so the final momentum has to be 0. Okay? That means these guys have to fly off 180 degrees apart exactly at the same speed to how many ever decimal places you want. So that's the kind of statement you can make. Okay. So you can conserve kinetic energy by giving them different velocities, but conservation of momentum says no. They have to have the same velocities, the same speed, and go exactly in the opposite direction. Okay. So see, now you got an additional restriction. All right, now, to review, the two main things that you've learned in the previous slides were the impulse momentum theorem. Impulse was equal to change in momentum. And the other thing was force was dP by dt. And if external force is 0, P is constant. Okay, so that's what you learned. Okay, now we'll switch gears and we'll talk about collisions. Any questions so far? Yeah, you guys understanding this? All right, now we'll study collisions. Okay, so I showed you 1D collisions, but now I'll show you 2D collisions. And okay, I haven't told you what center of mass is right now, but you'll learn soon enough. Okay. Elasticity. Okay, so watch for this crosshair. That's the center of mass. I'll make it collide, make these objects collide. And again, here's the total momentum. In this collision, of course, no matter what you do, momentum will be conserved. The total momentum will be conserved. And it's kind of hard to see, but the center of mass moves at a constant velocity. Okay. Okay. So here's another thing you can say. The center of mass velocity is constant in these collisions. Okay? In collisions, as long as no external forces act. Okay. So we'll look at types of collisions. If final kinetic energy is equal to initial kinetic energy, then the collision is called elastic. Okay. So this happens at all most of the microscopic collisions are elastic collisions. So there's 10 to the power of 28 gas molecules in this room, and they're colliding trillions and trillions of times a second. In every one of those collisions, kinetic energy is conserved. Okay? When you play pool, those are elastic collisions. If final kinetic energy is less than initial kinetic energy, then it's called an inelastic collision. This is what happens when two cars collide. Okay? If final kinetic energy is 0, then the collision is perfectly inelastic. When do you know any situation when this thing happens? I'm sorry? Okay. I can just cook up an example. So here are the pizza ball dough. Here's another pizza ball dough. You send them at each other and they'll stick together. If you send them at the same speed, they'll stick and come to rest. Okay? Two cars of the same mass can collide and they'll come to rest. If they come, if they're springy, they'll bounce back, but If final kinetic energy is greater than initial kinetic energy, then some form of energy got converted to kinetic energy. Okay, so it's more than likely an explosion. Chemical energy got converted to kinetic energy. So you can have a hand grenade sitting on the table and it explodes. Its initial kinetic energy was 0, and then the shards have kinetic energy. So in elastic collisions, kinetic energy and momentum are conserved. In an inelastic collision, only momentum is conserved. But momentum is always conserved. Okay? So here in collisions, momentum is more useful than energy in analyzing situations. Okay? So that's why we are learning about this. Here's why do you learn about new quantities when the old quantities are not enough to analyze situations that you encounter? Okay, so the sum of the momenta of the two objects before the collision is equal to the momentum after the collision. Okay, so the momentum before the collision, there's the momentum before the collision. This is momentum of particle 1 initially before the collision, momentum of particle 2 before the collision. So there is the sum. And here we are considering a 1D collision, and in this collision the two objects stick together. Okay? So if you have a collision like this, the final velocity is this. It has to be this. It cannot be anything else. Okay? So if the two objects stick together, the final velocity has to be this, and we'll do this lab. Okay? Now, see, this is pretty powerful. Have we told you what these things are made of? No, they can be made of anything. The final velocity has to be that. Okay? Momentum conservation forces the final velocity to be that. Okay? Elastic collision. What does this mean? What does an elastic collision mean?
Kinetic energy is conserved.
Right, very good. Momentum is always conserved, that's a given. So in a collision, momentum is always conserved. In addition, kinetic energy is conserved. Okay? So there is an additional constraint. So here is momentum conservation. Initial momentum of the two particles, final momentum of the two particles. That's equal to that. And in addition, kinetic energy is conserved. Kinetic energy of the final objects. Okay, this is only in one dimension. Now, so this is a quadratic equation, but using these two equations, you can manipulate it, and what you can get is two linear equations. Okay, so in 1D elastic collisions, these two equations are true, only for that. Okay, and the reason we are giving you this is now two linear equations are much easier to solve. I mean, much easier to play with than if you have a quadratic equation. Okay. Now let's see what is this thing saying. This is V1 minus V2. That is the relative velocity. So this is V1 minus, so this is minus or minus V2. So what this velocity is, if you're sitting on this guy, this is the velocity, this is the speed at which he's coming at you. That's what this guy is. Okay? So let's say you're going at 5 meters per second and this guy is coming at 10 meters per second in the lab frame. If you're sitting on this guy, he looks like he's coming at you at 15 meters per second, right? So let's say this is 5 meters per second. This is minus 10 meters per second. Then if you were sitting on him, he's coming at you at 15 meters per second. What is this guy? Negative of that. So now if you were sitting at him, he'll be moving away from you, okay? And it'll appear that he's moving away from you at 15 meters per second. So negative of negative 15 meters per second gives you that. Okay? So if two things collide in one dimension, in 1D elastic collision, if that object is coming at you at 15 meters per second, he'll go away from you at 15 meters per second. Okay? So that's what that thing is saying. Now we'll talk about 2D collisions. Okay? So here is this object colliding with that guy. Okay? Again, so here's the initial momentum of the system, and that should equal the final momentum of the system. Okay? Now in this situation, this has only an x component of momentum, so the final momentum can only have an x component. Okay? So if these two guys fly off like that, okay, so there is this guy, particle 1, particle 2. So the momentum of particle 1 in the y direction and the momentum of particle 2 in the y direction, they must cancel each other. Only the x components will add up to that momentum. Okay. All right, so anyway, so But in general, if they have both components, here's the x component of the momenta is equal to final x component of the momenta. Initial y component of the momenta is equal to final y component of the momenta. And if the collision is elastic, then kinetic energy will be conserved as well. So in 2 dimensions, for an elastic collision, you have to satisfy 3 equations. Okay? So the more equations you have to satisfy, the more constraints you have. Okay? The less freedom you have, so to speak. Okay? All right, so that's it about collisions. Now we'll talk about center of mass. Okay, so let's say I toss a ball. So I toss a baseball. What is the trajectory of this baseball? I'm sorry? Yeah, it's a parabola. Now I toss a baseball bat, and you see this is not a parabola. The tip of the baseball bat is not a parabola. The head of the baseball bat is not a parabola. In fact, it turns out that for an extended object, there's only one point that goes on a parabolic trajectory. And that's the center of mass. Okay? And that is the point as if you squish the baseball to a single point, that's where you would squish it to. Okay? So all objects have center of masses. Okay? And so we'll calculate the center of mass if you toss that object. So if you do a somersault, for instance, no part of your body will go on a parabolic trajectory except for your center of mass. Okay? And so the center of mass, so now we'll show you how to calculate the center of mass. Of course, for a uniform square object, the center of mass is that. For a bowling ball, the center of mass is at its center, at its geometric center. Okay? And so on. Okay. So now, if you wanted to find the center of mass for an object like this, what you do is you hang it from one point, and the center of mass is somewhere on that line. And then you hang it from here, and the center of mass is on that line. Okay? So the intersection of the 2 lines gives you the center of mass. Now, of course, for a 3D object, for a, let's say, a rock, you would have to hang it from 3 different points to get the intersection of 3 lines. Okay? Now, here's an interesting point. The center of mass of this system of particles is there. The center of mass of an object doesn't have to be within an object. So, okay, so here's a better illustration. Let's say you have something like this, an object like that. Its center of mass can be here. Okay? So the center of mass of an object doesn't have to be within the object. Remind me in lab Thursday, and I'll show you some objects whose center of masses are outside the object. Okay? Unfortunately, I forgot to bring it today. Okay? So if you have several point objects, calculating the coordinates of the center of mass is like this. The x coordinate of the center of mass is take each mass, find its x coordinate, multiply it, and then divide by the total mass. The y coordinate is take each mass, multiply its y coordinate, divided by the total mass. Okay? So this is how you calculate the x, y, z coordinates of the center of mass of a bunch of point particles. If you have a continuous object like this, and you want to find the center of mass of that, okay, you would do these triple integrals. Okay, so I'll write down one of these integrals. M is the total mass. Okay, and the x center of mass. And in fact, in your Calc 3 classes, you will be doing these triple integrals. Okay, have you guys,
Not yet, I'm not looking forward to it though.
but you're aware of it? Okay. Are your friends scaring you about them?
I don't have any friends there, so I'm just kind of waiting in anticipation.
Just don't make friends.
Okay.
Okay, so dm, the mass of this little piece, is the density of the matter at that location, okay, times the volume. And the volume is dx, dy, dz. Okay, this is in Cartesian coordinates. Okay, so based on the symmetry of the problem, you use various coordinate systems. Okay, so to calculate x and y coordinates, it's the density at a location, dx, dy, dz. Okay, so you would be doing those triple integrals. But this kind of stuff can be useful enough where they do these triple integrals for you. Well, anyway. Yeah. All right, so see, knowledge, this kind of knowledge can be useful. Mr. Fosbury, I believe he was at the University of Washington, I'm not sure. Anyway, in the 68 Mexico City Olympics. Okay, so the idea is the following. Okay, in a high jump, what you're trying to do is you're trying to raise your center of mass as high as possible. Okay, so here's the ground, there's the bar, and the idea is for you to cross over the bar. And in the past, people would jump like this. And so what you've done is you've raised your center of mass that high. And most athletes roughly are, have the equal capabilities, and most of them are able to raise it to that level. Now this fellow was smart. So he learned how to jump like this. And you see his center of mass is going below the bar. Okay, so he made his center of mass below the bar so he could cross this bar. While everybody else is jumping this bar, he beat the heck out of everybody. Did you guys understand that? All right, so anyway, this is a YouTube video, I believe, from the Mexico Olympics, but you can check it out. All right, it's 2:12. I want to finish this lecture. Okay. So what is Newton's second law? I'm sorry?
dp, dt.
Very good. F is dp over dt. Okay. So the net force was that. So this applies to a single particle, but it turns out it applies to a system of particles as well. Okay, so you have a bunch of particles. Let's say this is the force on this, that's the force. You add up all the force, that'll be the net force on the system. You add up their momenta, that'll be the net momentum of the system. The net force on the system is rate of change of net momentum of the system. Okay, so this equation applies to a single particle and it applies to a system of particles as well. Okay. So that's the total momentum of the system, and the net force on the system is rate of change of net momenta of the system. Yeah. The net force changes the center of mass acceleration. That's when the mass is not changing. Okay. So for a system whose mass is constant, it's the center of mass acceleration that you affect. Okay. And you guys saw the center of mass. I'll go back to that simulation for a second. Okay. So in that simulation, I showed you a collision and the center of mass was moving at a constant velocity. Okay. Okay, so I'm just going to show you the center of mass. Okay. So what does our equation tell us? If there is an net external force acting on the object, then its center of mass accelerates. In our case, we are not applying any external force, so this center of mass will have zero acceleration. Okay. All right, so external force is zero, so total momentum will be conserved as well. Okay, so just watch the center of mass. Okay, so that's a useful tool for analysis, and we'll watch it again, and this time we'll watch the total momentum as well, and center of mass velocity is constant and the total momentum was conserved as well. Okay. Okay. See, you intuitively knew this equation, so I'll tell you what. We've all watched fireworks. You see these rockets go up and you have an explosion. And have you ever tracked the remnant of a rocket coming down? Yes, you have. You've never seen it? Have you seen it?
I think so.
Yeah. So, what?
That piece that falls down.
Right. So next time, try and observe it, and you will know it because it's most of the mass is there, and you know it's going on a parabolic trajectory, and so intuitively you know where to look, and so in the dark sky you're able to locate it. Okay. So you know, the force acting is the force of gravity. It's parabolic trajectory, and that's where you'll track it. Okay. Do you know the closest supercomputer around here?
Our brain.
That's right. That's the most powerful computer in the world. It's more powerful than any computer in the world. It knows. All right. So now we'll talk about rocket propulsion. Okay, so this relies on rocket propulsion. See, for a rocket, there's no external force that's being applied. Okay. A rocket is a bunch of mini explosions. Okay, so here's the idea. Okay, let's say you're standing here on a frozen lake, you're wearing skis and stuff like that, and you have a bunch of physics books. You're at rest. Okay, so initial momentum of this system is zero. Now, if you want to move, what do? You throw one of your physics books, and you'll recoil. The total momentum of this system is still zero. You want to move faster, throw another book, and you'll move faster. Okay? So assuming you're not being slowed down, you want to keep moving faster, you keep throwing books. That's a rocket. You keep throwing hot gases out, you go faster and faster. After all is said and done, the total momentum of the entire system is still zero. Do you guys understand that? All right, so I'm just going to give you the equations quickly. I'm not going to derive stuff. Okay, so we'll consider a rocket in deep space. So here is the mass of the rocket, okay, and here is the velocity of the rocket. Now, if it wants to go faster, what does it have to do? It has to spit backwards. So it sends out a mass of hot gases, and the remainder of the rocket is going faster. So this is the momentum of the rocket before it spit stuff. and here is the momentum of the rocket after it's spit. But this momentum is equal to this momentum. Okay. So this guy is that guy, and this guy is that guy. See, now its mass is less, but its speed is greater. There's the momentum, and that's the momentum of the stuff that you spit. Okay, those are the that's the exhaust velocity, and the exhaust velocity is given relative to the rocket. Okay. And so this is the velocity of this stuff in the lab frame. Okay, if you rearrange all of this, this is what you get. You rearrange all of that, you get this, and then you integrate that, this is what you get. What this is, so in deep space, this is the final velocity of the rocket, this is the initial velocity of the rocket, this is the exhaust velocity, that's natural log of initial mass of the rocket divided by final mass. Isn't this guy 0? Shouldn't that be 1? And that would be 0. No, for a rocket, your initial mass is about 10 times your final mass. Okay, so this guy is, okay, so natural log of 10. Okay, so if 90% of your weight is fuel, let me calculate log of 10. 2.3. So if this is 10, this is 2.3. So 2.3 times the exhaust velocity is your final velocity if you start off from rest. Okay, so that's what that is saying. Did you guys understand that? So one of the things that the rocket has to face is, so here's a rocket sitting on the launch pad. Let's say it weighs 1 million pounds. Okay, this is the thrust of the rocket. So if it has to lift off, the thrust had better be greater than the weight. Okay? And so for most rockets, so I'll show you. For the space shuttle, okay, so the thrust was 8 million pounds, 3.55 equivalent of 3.5 times 10 to the 6 kg, and the weight was 2 times 10 to the power 6 kg. If you divide that by that, thrust to weight ratio at liftoff, here's a standard thing, so here's a good rocket. Okay, so what does this number mean? It has a thrust of 1.8 pounds for every pound of weight. Okay, if you have a thrust of 1 pound for every pound of weight, you're not going to lift off. Okay, you're barely going to lift. Huh? That's right. But then you will, if you have a stable hover, then eventually you'll fly. Why?
Because the mass is getting smaller.
Very good, my friend. See, that's what I want you're thinking. He's half asleep, but he's thinking. He's tired. He's not half asleep. All right.
Fair enough.
What's that?
I said fair enough.
I can see you're tired, my friend. All right. So anyway, this is the rocket thrust. What the rocket thrust is mass times this is mass times acceleration of the rocket. Okay, and that's equal to, this is the exhaust velocities of the gases. What is this? dm by dt. I'm sorry?
Changing this.
Mass of what? Okay, why is it changing?
Fuel.
That's the burn rate. Okay, so that's the rate at which you're burning fuel. So that's the rate at which its mass is burning. So you want greater thrust, you either choose a fuel with a great exhaust velocity or burn fuel at a faster rate. Okay. So the larger the rocket you have to launch, the greater the fuel burn rate you have to have. Okay. Now, of course, we are interested in launching rockets from the surface of the Earth, and so this formula which was good in deep space in the absence of gravity, gets modified to this, okay? So the final velocity is initial velocity. There's that original term minus g times, because, so your change in velocity gets decreased by this much because of the gravity, okay? So gravity times this is the flight time, okay? Or burn time. Okay, well, I'll just quickly give you numbers on, so, I don't know, well, some of the, well, you guys all have all heard of this space shuttle. All right, it flew about 109, 10 missions, or 12 or 13, anyway. It took about 8 minutes to get to orbit. These were the solid rocket boosters. This was the main fuel tank, and so on. These solid rocket boosters burned for 2 minutes, okay? So you have to have boosters on the launch pad because it was too heavy. And once you got light enough and you got high enough, those boosters were ejected. Yeah. So there's the, what did the space shuttle burn? What was the fuel?
Hydrogen?
Hydrogen, okay? What's that?
Sorry, just hydrogen and oxygen.
Well, oxygen is when you burn something, so there's the fuel, liquid hydrogen. And there's the liquid oxygen. Okay, you're burning fuel at such a rate that you can't just use the oxygen in the air. That's too little oxygen, so you have to carry your own oxygen. Okay, so,
Somewhere that doesn't have oxygen.
what?
Plus, you're going somewhere that doesn't have oxygen.
Right, yeah. So, but, I mean, even at low Earths, even scramjets have to compress the air. Okay, so, anyway, so you have to carry your own oxygen, okay? So, you saw that for the thrust, mdv by dt, it was ve times dm by dt. This was the burn rate, and this was the exhaust velocity. So here are some of the exhaust velocities. So this is the main engine of the shuttle. These are the solid rocket boosters. The main engine exhaust velocity was 10,000 kilometers per hour. So the gases were coming out. VE was 10,000 kilometers per hour, about 3 times the speed of a high-powered rifle. At these exhaust speeds, the main engines were burning fuel at a rate of 1,200 kgs. So the hydrogen was being burnt at 1,200 kgs per second. 1,200 kgs per second is the weight of 12 small cars a second. That's how much. Okay. And that's not even the solid rocket boosters. Each of the shuttle solid rocket booster burned 5,000 kilograms of propellant. Okay, so at launch pad, 1,200 plus 10,000, 22 little cars were being burned per second. Okay. And look at this. There's the shuttle. This is Starship. More than twice as powerful. Falcon Heavy is that. This is 5 times as powerful as the Falcon Heavy. Okay. So this was named BFR.